All right, so this is my presentation. So one thing I want to say is just bear with me a little bit, because to get you used to this type of stuff, we're going to have to go through assembly language, and it is boring. So that's half the presentation. The other half's really fun, I promise. So anyway, who am I? You heard I'm just a guy who likes security. I'm a PHP Python application developer, part of DC 801 group. I also help run 801 Labs. Just a little quick legal disclaimer. I'm not responsible for anything dumb you do because you learned it from me. So don't blame me. So one thing I wanted to talk about is that when we think of binaries, when we think of executable files, we kind of think that's it, right? Like, we don't have the source code, we don't have any of the documentation, all we have is this binary where, well, we're just pretty much stuck and there's nothing that we can do. In that sense, you know, I always love this quote from the Matrix, is that there is no spoon. There's only your own inhibitions or your own perception of reality that's stopping you from doing whatever you want to do. I mean, there are physical limitations on computers, but it boils down to everything's a file. Everything's just data, or data being interpreted by a processor or a system. So we talked about this a little bit. One of the misconceptions people think of when they think of software is just how it's finished when it's in a binary form. I mean, this is convenient for companies too, because when they distribute software, they're like, they expect you to not mess with it. There are techniques and things they can do to make it more difficult for you to modify their binaries or modify their software after it's being deployed. But we're not going to go into those today. We're just going to give you a brief introduction on how to modify binaries and learn some assembly language. So a couple misconceptions about assembly language is it's hard to learn. Yeah, it is difficult, but I mean, so is any other programming language. Anything that you work hard at, eventually it'll start clicking. There is a huge learning curve with assembly language, but if you just kind of sit down and do a little bit every day, maybe a half an hour, just reading some of it and learning it, you can kind of get familiar with the patterns and the concepts and the understanding that's required to read assembly and use it. Another thing is you look at the assembly manual for Intel syntax, and the books are like this big. This is one book. Like, Ray Ronan brought in the Intel assembly book, and it was like, I thought he brought in like 6 for everybody. No, it was one book. It was like tomes. Yeah, it was like this tall. I should have brought it in, it would have been good. But like, out of all of that book, you only really need to know 14 instructions. Consist of 90% of all code. And so once you've gone about 20 or 30 instructions, you probably covered every scenario that you'll encounter with any compiled code. And the only reason you need this giant tome is if you're trying to do something special or outside of that realm. Also in that case, when you're writing assembly, the assembly you write for one architecture does not transfer to another architecture. So if you write something in Intel 86, it's not going to go to an ARM processor, it's not going to go to a PowerPC, you kind of have to rewrite it for those. And that's one of the reasons why the compilers were invented, is so that you could write programs in one language and it could be ported to different architectures. So, quick introduction into assembly language. It's a complex, for Intel assembly language in x86, we're going to talk about 32-bit instruction set. I will talk a little bit about 64-bit, but it's easier to just start with 32-bit and then move up to 64-bit once the concepts are kind of solidified. Like we said, it's a complex instruction set. It has executable instructions and assembly directives. It consists of 3 types of statements there: the executable instruction, the assembly directive, and then macros. So when you start learning assembly language, the thing that you need to memorize pretty much is this chart. You need to be able to go from decimal to binary to hex. Now, that being said, that doesn't mean, I have to memorize it today. But after a while, if you do this enough, it'll just become easier and easier to remember all of these things, and just being able to be like, X0E is 11. I was looking at that actual specific one the other day, and I was like, yeah, that's hex, right? Because that's 11. I'm like, is that 11? And that looked a little weird. I'm like, yeah, it is 11. I wasn't actually expecting the value to be 11, but then I forgot about the extra space that C has for strings with the null terminator. So it's a good idea to start, if you want to really get into this, just kind of memorize the conversion. So another thing you need to take into account is that in assembly we're going to talk about binary, and we're going to talk about bits and bytes and words. Those are the ones that come up a lot. And the key to remember is that one bit is just one on and off. A byte is 8 on and offs. So it's 1 byte is 8 bits. One nibble is 4 bits, but they don't talk about nibbles very much, but you do work with nibbles a lot. So another thing is, so you have double, you can have word, and you'll see double word, so that's just saying that you have, so a word being 2 bytes, and then a double word would be 4 bytes. Making sense so far? Pretty basic stuff. So next we have Intel syntax and AT&T syntax. The main difference between them is just how how the language is formatted. I'm going to be talking in Intel syntax today. AT&T syntax is not, there's not a big difference between them. I mean, there's nuances. The one that's confusing is that they're in reverse order of the instruction set. So here's just some simple syntax. We'll go over the instructions in a little bit here, but we're just moving the value of 1 into an EEX, and then the other one here we're moving the value of 1 to EEX, and you see the order is flipped, but it's the same instruction. So just remember, if you're seeing a bunch of dollar signs and percent signs, you're in AT&T syntax. If you're not, you can use Intel syntax. So a couple important things to think about with the binaries is the sections of where the data is located. The data section is where your static variables are going to be and everything that's declared beforehand before you compile. The BSides section is for declaring the individual variables. And then the text section is the important section. That's where the actual instruction code is located. All right, we good? Anybody lost? Have questions? Yeah. I haven't really looked because it hasn't been really important so far to me, but I believe that section just has the declaration and just kind of like a symbols table that defines, okay, this when you say int x equals this, it's defined here, and then you use that variable throughout your program. So we have registers. So registers are kind of the heart of assembly language, and then every register kind of has a special purpose, and this purpose is arbitrary. It's basically just whatever, whoever the Intel designer decided that's what we're going to use this register for. They're all technically the same physical hardware, and they're just different sections of the CPU that store data. And one of the more popular ones is EEX. EEX is always going to be the return register. So later we'll talk about calling procedures, but everything, basically when something calls something and it returns, it's going to store EEX. So it's kind of like the magic box where wherever you're expecting something for something you call, that's where it's going to be. EBX being the base pointer. The ECX is used for counting and looping. Like I said, these are just general conventions. There's nothing enforcing this, but what they're saying is that when you're writing code and you're doing some looping or operations, EDX is a recommended one to use. EDX for IO pointers, EDSI for source pointing for string operations, EDI for destination pointer of the string operations. And then so ESP and EDP and EIP, these are important because they deal with the execution flow of your application. So ESP is the stack pointer. It basically points to the stack. We'll talk about the stack in just a little bit. And EBP is the stack frame base pointer. So it's kind of we'll talk about the stack and go over that in a little bit. But EEP is a cool one because EEP is actually the next instruction. So in a lot of buffer overflows and other things that when you want to get control of EEP, if you can figure out some way to get your code into EIP, you can do exploits, do other things. Like we said, in 32-bit registers, they are 32 bits long, and 64-bit machines, they're 64 bits. Excuse me. So this is just kind of to show you the sizes of each register. The R is a 64-bit version. So we have EAX as the 32-bit, and then we can also see references to the lower versions of memory, like AH and AL here. And basically that's saying is that we're instead of looking at the entire register, we're just going to look at a small section of the register here. So we're just going to look at these, if we said AL, we're going to look at these first 8 bits. If we say AH, we're going to look at these 8 from 16 bits. And so another important register is the eFlags register, and this basically, anytime you do any operation, depending on what that operation does, it will flip these bits, and this is important for controlling execution flow. We'll talk a little bit more about that later. So for the stack is an area of RAM that is used to store variables and temporary memory. The stack is created when it's loaded. So this is where you're just going to push variables, and if you need to store a register, you're going to be pushing it on the stack. Does anybody have any questions about anything I've talked so far? Any confusion? Want me to repeat something? Good. Okay, so with the stack, ESP register is the start of the stack frame, and EBP is the register that ends of the stack frame. So ESP is basically the stack starts here, and the EBP is, okay, we're going to grow EBP. And then we'll also see that EBP will put to ESP when we do a stack call. So anyway, the stack is just basically we're going to push data on and we're going to pop data out. Talked about that. So here's kind of a visualization of the stack. We can see here that anything below EEP is actually going to be the current stack frame. So if you can think of this as like your C code, this is where you would initialize, this is where all of the local variables in your local C code or in your function are being declared. And then anything above here is anything outside of your function. So this is why functions can get data outside of themselves, but other functions can't get data inside of, when they call another function, they can't get that data, because every time you do a function call, it's creating this new stack frame and it's allocating more space on the stack. And then we have kind of a visualization. Does anyone have any questions about this? We all good? So this is a common section of assembly language that you're going to see a lot when a stack frame is called. And so basically we have this function called test, and then we're going to push EBP onto the stack, and then we're going to move EBP into ESP. And so you'll see this every time that there's a new function called or any time we're doing a stack frame setup. And then another thing to kind of keep in your mind is there's calling conventions, and these can switch. So if you have the call E save registers, these are basically, it's that the callee has to take care of all the registers. So if it's working with data, it's got stuff in the registers, and it's like, I need to call this function, and you're using the callee save registers, then the callee, or the caller save registers, then it's responsible for taking care of EAX, EDX, pushing them on the stack, and then popping them back off when it returns. And then the same for callee registers, where it's like, okay, I called you, the callee is like, oh, okay, I need to take care of all of these things and then put them back before I return. All right, so here we're going to start getting some more of the fun stuff. So we're going to learn 9 instructions today. There's the NOP instruction. This is a great instruction if you want to just kind of overwrite some memory. And you can, like if you go to we'll show this later, but if you go to a specific point in memory and you can just NOP it out, And so when the instruction set gets to that section of the memory, it'll just continue just doing nothing and then it'll continue on its way. The call instruction, it calls another section of code, so it's basically like calling a function. So when you see a call, it's going to go to a different stack frame. And then we have return to the Mac frame, move, push, pop, subtract, add. LEA is an interesting one because it's load effective address. Basically, it pulls information out of memory and puts it into a register, or you can push it onto the stack. So we have another 5 instructions: copies the frame pointer, leave, copies the frame pointer to the stack pointer, test. So test and compare and jump not 0. These are your if statements. So with these instructions, like test, you'll see test EX, EX. You'll be like, okay, why am I testing the same register? This seems silly. Well, what it's actually doing is test does an and it ands both of the registers together to see if they're equal to 0. So you do a test, and then depending on the jump not 0, let's see if it is 0 or if it's 1. It'll return 1 if anything else is if it's not the same. Brain fart. Okay. Makes sense, right? Question? So we've just right there, we've learned, 14 instructions. So you've learned pretty much a good amount of instructions you need to do just about anything you want to do with assembly language. And so I've included the operation code here because the operation code is important when you're actually modifying binary, because you're not going to see NOP, you're going to see 90 in hex. And the thing is when you're modifying your binary, you need to find the specific code section, and basically you're going to look at your disassembly and you're going to look at this hex binary and you're going to say, okay, I believe this section is actually correlated to this instruction set, and then you go in through and make your changes. Just a quick talk on symbols. Symbols are basically just a mapping of the addresses that are used during the linking process to resolve references to functions. So basically it's just kind of something that the linker uses to say, oh, when you said test, it's actually to this memory address. You can view the symbols with NM. It's a program that comes installed with GCC and other Linux tools. Another thing to just kind of mention briefly is the ELF instruction executable link file. Basically, it's just the format that the binary is in that Linux can understand so that it can execute it. Another thing to just quickly glance over is big Endian, little Endian. This is basically the order in which you read the least significant bit and the most significant bit. So in this example, 0001 is 128 in big Endian, and little Endian 0001 would equal 1. So depending on your architecture, if it's big Endian or little Endian, it's important because you want to read the data correctly. Yeah, so another kind of confusing thing is in Intel, little Endian on registers, big Endian in memory. So when you're reading memory, it's in big Endian. When it's actually being used in registers, it's little Endian. This is just kind of visualization. And the thing that's most confusing about this is that it's not reversing the bits exactly, it's reversing the bytes. So 0A being in hex, being 1 byte, isn't reversed, but the order of 0A and 0B is reversed, as you can see here. All right, we got through all the boring stuff. We good? Yeah! Woo. All right, now to the actual meat of the presentation, the fun stuff. If you're still confused, I'm sure I probably screwed something up or said something incorrectly. Most of the stuff I've learned in open security training, they have a really great course. It's a 2-day course. It's all free videos you can watch on assembly language. So you can just go there and get more information if you're still confused or just like, I didn't understand anything. It took me a while to kind of get used to this stuff, so don't, if you feel like, this might not be for me, it's just one of those things you just got to spend time on. So, quick setup for Kali. So I did all of this in Kali. I actually ran all these examples to make sure that what I was saying is true. To compile 32-bit binaries in Kali, you need to have the GCC multilib, and then you just compile M32 there, and that'll compile a 32-bit binary. And so another kind of useful tool to have is NASM. NASM's installed automatically on Kali, but these are just some other assemblers if you want to play around with them. Another very useful tool is object dump. Object dump basically will take the binary and break it out into its hex version and its assembly version. So you can use object dump to kind of just break everything out, and then you just take the sections of code that you're most interested in. Alternatively, dump bin is for Windows, so you can use dump bin to do the same thing as object dump. So this is Hello World in assembly. So this is everything that you need to run Hello World in an assembly language. And basically all you do is you have your start section, and then your global start here, your text section, your data section here below. And this is a little bit misleading because you're like, oh, these are instructions. These should correlate to actual binary instructions. There's actually micros in here that NASM understands. Like this bottom part here is a micro where it's actually going to take the length of the DB text hello world and actually compute that and then stick it in the binary, which I'll show again. So we just run NASM elf hello asm. We get an elf file. We link it with the linker here. We tell it's an elf i38.6. Say hello. We have an executable. So let's take a look at the object dump of that binary that we just created using NASM. So as you can see here, the instructions are actually completely different from the NASM instructions. And all we have is just a move. So we're going to move the value of 11 into EDX. We're going to move ECX, this value into ECX, which this value here of the 80490A0 is the actual address of this text string in memory. So it's basically just like a pointer in C or C++. And then we're going to put the value of 4 in EAX, and then we're going to call, this is a kernel system call when we call int86. So what that does is it calls the kernel, and depending on our registry settings, it's actually going to do different things. So this is that entire hello assembly language NASM assembled binary. So this is, you can visually see, you have seen hello world in binary, or hex, I guess is really what it is, I should say. So we can see that we see the elf string up here, we have the hello string, we have the text data section, the rest of it's just pure hex, looks like complete nothing, right? So let's go back to that system call. So if we were doing something in C, we'd say syswrite. We have an unside int, which is the file descriptor, is basically the location the file, a constant char, which is a buffer, and then the size. So in our NASM instructions, basically the length was EDX, was the third argument. The text section was a pointer to the message, and the first was the file handler. So we're basically saying here, write the file out. So our instructions are here in assembly, and we call this the system call here int086. And let's see, going back. And then the 4 was the system write. So we're saying when we called int80 and we had EX set to 4, we're calling system call 4, which basically says go look in these registers, and then we said use a standard out to write output to the screen. And then again, here's hello world and ASM. You can use ML64, which is brought in with Visual Studio. You can do the hello world in Windows World. We all good? Making sense? Questions? Yeah, so like In these registers here, we can see that these are basically these are all the variables that I'm passing to the function. So we're basically, instead of saying, writing it out like we would in C here, so we have the C syntax where we'd say system right, and we'd pass in all the function variables, we're just putting those values in the respective registers and then calling the kernel to actually execute and write to the screen. Okay, so this is a simple C program, the hello world. And so this is an object dump of that simple C program. And there's actually a lot of stuff that the GCC will add to the binary. And so it'll be a lot longer than this, but this is basically just the important parts of the code that I'm highlighting here. So in main, main eventually gets called. So you always think like, oh, main's where everything starts. But actually there's a bunch of preceding steps, and then eventually it'll get to main. But that's basically where your code starts, is at main, after it's done all of its setup and all of its management that it's going to do. And so before we were talking about the symbols, so when you're starting to do this and you're using basic binaries, you just go and look for main. You got to find your starting point, right? Like you would with any program. If you had a bunch of source code and you were starting to okay, I need to learn this code, you'd say, okay, where does the execution start? What does it start doing? So you go and look for main, and then you can start stepping through these instructions and going through the binary and kind of reversing it. So we'll go over this really quick. So like we saw before, this is a stack frame setup. So you push EBP, move EBP on ESP. So these registers, remember, they control where the beginning of the frame is and where the end of the frame is for this function. So we have this area that grows and shrinks. Now when we increase the stack, we're basically declaring variables. So inside your function you say int x, int y. You're just going to see that the stack is going to be pushed down, and then values will be put on the stack to represent those variables. Also, it'll also put that data into registers sometimes if it's just a temporary variable that's not being used outside of the frame. So with this, we just push on the frame, or we push EBP, ESP. We're going to AND ESP with 000F. Not quite sure what that's doing there. But so you see down here that we're going to call test, which is actually this memory address here. And so the symbols are your representation for you to be able to read this, but the computer just says, oh, I'm going to go to this memory address and I'm going to start executing this code up here. So then it hits this code area, does what it's going to do, says, okay, I'm going to print hello world, and then we're going to return beef. And so one thing you can do when you're doing reversing and you're just working with binaries is you can put in just easy to recognize hexadecimal representations of integers or anything. So this is I put in beef here, and then I can see beef is actually over here in this move instruction. So when it returns, this function returns, it's going to move beef into EAX. This is important because EAX, like I said, is just the basket where everything looks when it comes back for the function. So if this function was of type int, EAX would have the return value of whatever beef would be in decimal form. And so we can see that when we return main, we're returning 0FF to the previous function that called main, which so when you return, you can have exit codes and stuff like that. So basically you can just see even main itself put stuff in EX and then returns back to the main section. So one of the good tools to have when you're doing binary analysis is PETA, Python Exploit Development Analysis for GDB. One key thing to know about PETA is that it doesn't work with Python 3, and newer versions of GDB use Python 3, so when you're installing it, it works really well with Kali because I think it uses the older version. So you can just get it installed and run it. And this is what PETA looks like. And the great thing about PETA is it gives you a visual representation of what's actually happening inside the binary when you're running it and you're executing it. So you can see here, you can see your stack down below. This is that word actually says stack. I know it's hard to read. This is just a screenshot. And then here's your code, so there's a section of memory you're working with. And then here's all of your values and all of your registers. If you don't have this, you have to use GDB, and GDB is just a command line written, I believe, mostly by Richard Stallman, and he just has a command line, and you're like, okay, I need to look at EX. You type /XX and look at EX, look at the value. Here you can just type context, and it just gives you a brief overview of everything that's going on. So, quick introduction to GDB. We have the run command, the break, and then we want to set the disassembly flavor, because everything in Linux is going to default to AT&T syntax, AT&T syntax, yes. So we want to set our disassembly flavor to Intel. We use the disassemble function to look at the actual instruction set on the function or the area we're looking for. We set breakpoints so we can stop execution. Do info registers will tell us what the registers are doing. Info breakpoints just shows us all of our breakpoints. So how many people here have used a debugger? So if you know what stepping is, right? You hit a breakpoint, you stop, execution stops. Okay, that's critical for doing this because if you run it, it's going to go way too fast for you to do anything. So this is GDB disassemble main. So we say we want to see what main looks like when it's disassembled. And this little arrow here is the execution point. This is basically, if you hit a breakpoint, this is where you're stopped in memory. And the info registers, info breakpoints. This is a useful command. It's the x/x. It basically lets you look at the register in a binary format or hexadecimal format. And then print EX lets you print the actual value that's stored there. And so if it's a pointer, if you do x/x, it'll give you the pointer. If you do print/x, it'll actually follow the pointer and then follow the memory to kind of see if it's a string or something, it'll follow it to the null terminator and give you all that information. Okay, so this is our example program that we're going to modify. So we're going to actually modify some code, make some changes, and change how this execution is. And so basically what this is, we have our test hello world. We have this hidden function, which is not called by main at all. It's just in the binary. And then we're going to call test. We're going to sleep for 15 seconds. And then we're going to compare argv1 as the variable that we're passing to main to see if it's secret. If it's secret, we know we've got it. If it's not secret, we're sorry, you missed it. So we compile it. And then we open it up in GDB and we do run test. And then basically what this does is the run test is going to pass that test argument to this binary as argv1. And so we say, hello world, sorry you missed it. And then we say inferior process exited with 0337. Which if we look at the code here, I said, oh, return 0xff instead of 0. So one thing that kind of gets confusing is like, all right, I'm going to go into memory, I'm going to change something. Like, oh, it won't let me. Why? Well, with the GDB, you can only modify the binary if it's running in memory. So before you actually go through and change stuff, you have to set a breakpoint on main or set a breakpoint in the section that you're interested in, run it, and then you can modify the binary itself. So here we're going to break main. And then one other thing is you can break on specific areas of the binary. So if when we saw the disassemble main in the text section, you can see, okay, this memory section over here, like this 08048-4BC, we can put a breakpoint specifically on there so we're not going through all the execution. So we disassemble main, and we're going to modify the binary here so that we don't, because the 15 seconds is annoying, we want to change it to 1. So we're going to just make a very slight, small change to our binary. And so you can see here, we disassemble main, so the left section, let's see, wait a minute for you guys. So the first section over here is going to be the before, and this is the after. So if you take a look, we're passing down here, we're passing F to ESP. And if we look, just before we do that, or just after we do that, we're calling sleep. And so I wonder if this variable is actually controlling how long we're going to sleep for. So using the set command, and the set command is where all the power comes in and modifying the binary with GDB. We call set. When we call set, we put it in parentheses, we put a star, we go to this memory address over here, the 0804844BC, and we say we're going to set you equal to C7. What that's going to do is it's going to change this 0xF to 0x1. And then we run the code, and we show that, okay, it's only sleeping for 1 second. So now that we've modified the binary, with GDB, we want to go through and actually modify it with on the hard drive and actually manipulate the binary there. And so what we're going to do, so this is what the value was before on the memory address at that location. So it was 0F2404C7, and we modified it to 01. So we see that we're just changing this F to a 1. Does everybody get that? Makes sense? Very quick, easy change. We keep the rest of it intact because the rest of this information is actually the hexadecimal representation of this instruction. We change F to 1. Here we can use the exam and just kind of see what portion of memory does what. When we do x/I, will show us the instructions. So this is useful when you're kind of developing your modification for your binary, because you can examine it, change it a little bit, and see what instruction set it's going to generate. And so once you've gone through it in GDB or gone through it in a debugger, then you can go back and in the binary itself using vim. So you use vim and you call xxd, which will change it to, xxd basically does what object dump does, but it gives you a hexadecimal representation of the entire binary. You go through and edit it, so you go through and find the edit that you want to make, and then you use xxd to retake that binary. So when you do edit in xxd, you don't longer have a binary, you just have a text file. And then you need to run it back through xxd to create a binary. And then we'll see here, and we can do a diff to see what the actual differences are. So when you're in xxd, this is what you're going to see, right? You're going to see an address here, and then you're just going to see a bunch of hex grouped together. And we've made, so the slight change we've made to this binary is we've changed this F to a 1. And somehow it dropped this 0A. I don't know why. It's weird. So we can see here that we've just made a slight change to the binary. So we found where this 240F, or the C70424F correlated in the actual hex editor. And we made the slight change, and then we wrote it, and we can run it. So at that point, we're just changing a slight variable. Now if we get down to if statements, you have jumps. Now if you want to, change a jump, you can just, there's a couple things you can do. You can try and you can try and nop over it, or you can just change the instruction. So what we're going to do next, instead of, because let's say we don't know secret, we're going to change the binary so that it says you got it for everything that isn't secret. So a quick note on jumps. You'll also see jump not equal and jump not 0. I think I got these backwards. I'll have to double check again. But basically just remember for jump not JZ and JNZ that there are two names for the same thing. And so what these jumps do is, depending on the E flags, if you go back to the E flags, depending on what operation you did before you're doing the jump, you're going to have flags that are going to be set. And so to modify the jump, we need to know what flag is going to be set depending on what situation. So here we have JNZ, and then the opposite is JE. So we go through, we examine the memory. We see that the instruction here ends in 74. we know 74 is the opcode for J and Z. If you go back earlier in the slides, we changed 74 to 75. And then now every time we run the binary, no matter what we put in there, it will say you got it. So if we go back here to the instructions, we've now changed this if statement to say anything that isn't secret will actually give us the you got it string. I'm done? Okay. All right, I am out of time, so we'll just talk really quick about calling that hidden function. I'll publish these slides so you can go over them in more detail, but basically you just run these instructions, change that little section, and you can change the code execution. With GDB, you can just call the hidden function itself. So you just say call, and it'll actually run the function. So you can run functions outside of their actual execution settings. So you can easily see with just some simple modifications, you can get in there and kind of make changes to binaries. And then here's some more references and stuff if you're interested. And that is it. Thank you.